In the last video, we talked about constant velocity motion. In this video, we want to analyze the scenario of constant acceleration. And so similarly, we're going to do this in the graphical way first. And so let's start from the A versus T graph this time, obviously, because we're looking at constant acceleration. So that is going to be an example of constant acceleration, right? I could have drawn it above the above the time axis. I could have drawn it below it, right? Whatever. But this is some negative value, and it's just constant, right? No matter what time value you pick, you're always going to get the same acceleration. And let's just say, for the sake of this example, that this happens to be negative 9.8 meters per second squared. Now, maybe that's familiar, maybe that's ringing a bell for you, maybe it's not. That's okay. I'm just going to give you that number, and we'll get to what that means in a minute. But that's just happens to be the acceleration, okay? Now, how do we get a negative value on the A versus T graph? Well, a negative value on the A versus T graph corresponds to a negative slope on the V versus T graph. Now, note that I am having it cross the time axis. It doesn't have to. It could start from there, right? It could go from there to there, right? It doesn't actually matter. I am having it do that for the sake of this example because I want this to be the most general example that there is. Okay, now I'm going to point out one more time, as we have previously, this crosses the time axis. And so we went from the positive part of the V versus T graph to the negative part of the V versus T graph. That means that we turned around. So turned around. Whatever direction it was going to begin with, it came to a stop and it started going the other direction, right? So it's going in one direction up until here, and then it comes to a stop, right? It's slowing down to a stop, and then it's speeding up in the negative direction, whatever that opposite direction is, okay? And once again, this has a negative slope, and that is how we go from negative slope here to negative value on the A versus T graph, okay? How do we get a negative slope on the V versus T graph? Well, this one might take a little bit more work, but let's just start here. We're gonna go, this is some double positive value, right? This is some less positive value, and then 0, and then this is some negative value, and then this is some more negative value, right? And so that's kind of, so we start with this, what I'm calling a double positive, and then we go to a single positive, and we go to 0, a single negative, and then a double negative, okay? How do we represent that on an X versus T graph? Well, we need something that's double positive, okay? Well, a double positive means it's going up a lot, and then it slows to a single positive slope, and it slows to a slope of 0, it slows to a negative slope, and then a double negative slope. Sorry, I should slows to a negative slope. I should have said it went from 0, it sped up to a negative slope, and then a more negative slope. Okay, because if we go from 0 to negative, all the negative is telling us is a direction, right? It doesn't tell us anything about the speed of the object necessarily. It just tells us the direction of the object's motion. Okay. So let's prove this here real quick. So we have a double positive, we have a less positive, we have a 0. Draw this a little bit more over here. And then we have a negative, and we have a more negative. Okay. Now, I didn't line these up perfectly, but you can see that this 0 does line up basically with where it turns around. That's good, right? Because the object is traveling, you know, it's going further and further and further away from the origin until it reaches some max distance away, and then it turns around and comes back. Okay, that's what's going on. So that is where it turns around. You can see that this positive does correspond to that point right there, right? You can line all those up. This corresponds to here. This one corresponds to, right, that negative corresponds to that point, right? So you can see how these graphs play into each other, right? This is all very much connected, and this is constant acceleration motion. Okay. Why did I say negative 9.8 meters per second squared? Well, that is the acceleration due to gravity. So acceleration due to gravity, and I'm just going to call this AG for now. A sub G is equal to negative 9.8 meters per second squared. That is the accepted value of the acceleration due to gravity. Now, sometimes we use negative 9.81. Sometimes you can use even more decimals than that. but this is sufficient. Negative 9.8. Sometimes we just say that the acceleration due to gravity is negative 10 meters per second squared. Right? So it just depends. And the negative is only telling us the direction. So if you just want g, which is really the acceleration due to gravity without any direction necessarily attached to it, g is that 10 meters per second squared, or I should say 9.8, right? I'm going to say 9.8 meters per second squared, about 10 meters per second squared. All right, that's the squiggly line, equal sign, right? It's about. Okay. So this would be basically the idea of I throw a rock in the air, and at the second I let go of the rock, and I'm throwing it straight up in the air, right? No angle, right? Nothing like that. I throw a rock straight up in the air. At the second I let go of the rock, that's t equals 0, right? That's this origin, okay? And then I let it fall back into my hand, and at the moment that I would grab it, the time, right, the graph stops, okay? And so the rock is going up in the air, and it's very, very positive, very fast. But then obviously it slows down until finally it comes to a stop. Now I can't draw arrows right on top of the ones I just drew, but you can see it comes down and it gets faster and faster in the negative direction. Right? That's what happens when you throw a rock in the air. Not hard to imagine at all. Right? This is very, very common. And so this set of graphs is basically the set of graphs that you get. It is the set of graphs that you get for any object experiencing some sort of free fall motion when you throw it up in the air and then let it fall back down to where it started. Okay. So that is constant acceleration. Anytime that an object is falling under the influence of gravity and nothing else, we have constant acceleration motion, and that negative 9.8 meters per second squared, that's where it comes in, right? It is right down there. That is the constant acceleration. Now, let's talk about equations. Equations. First one to keep in mind is that x final is equal to x initial plus v initial x times t plus 1/2 ax t squared. Okay. This might seem like a complicated equation, but let's divide, x final, or let's subtract x final minus x initial, and then take that to the other side. So 0 equals negative delta x, right? X final minus x initial is over here on this side of the equal sign. We're going to subtract it over. Doesn't really matter. I mean, it does. It's important, but let's just say 0 equals negative delta x plus the initial velocity in the x direction, which does change now, right? This changes now. So we need these subscripts, times t plus 1/2, and then whatever that acceleration is in the x direction times t squared. Now here's the thing. I'm actually going to erase that, right? That's all I'm saying. That's all the equation is saying. But I'm also going to write it in this form right here. Y final equals y initial plus v initial y times t plus 1/2 ay t squared. Why am I writing this? Well, because usually we let the y-axis be, this positive y, negative y. Usually when we throw a rock in the air, we use the y-axis to tell its motion. So oftentimes you'll use this version of the equation instead. Both of them are good, right? If you have a car accelerating at a constant acceleration on the road, then maybe you want to use x because, we're used to x being that direction, right? If you're throwing a rock in the air, perhaps you want to use the equation with the y's in it, right? It actually doesn't matter, right? You could call this direction positive x and negative x, right? There's nothing wrong with that. You can use either equation for any constant acceleration motion. Sometimes one of them is just preferable because it might help you, physically understand what's going on a little bit better, okay? But those two equations are actually one and the same, so I'm just going to call that 1. And this is the kind of equation you would want to use to find the amount of time that something is, that something takes to fall, for example. So if you have a certain height that an object is falling, a certain delta y, you have an acceleration in the y direction, probably negative 9.8 meters per second squared, and then you have an initial velocity in the y direction. If you have all of those, then you're probably going to be asked to solve for t. Okay, so that's just an example there. Now, another equation that we have is that velocity v final is equal to v initial plus a times t. Now note that we could write this v final in the x direction is equal to v initial in the x direction plus ax times t. You could also write that v final in the y direction is equal to v initial in the y direction plus ay times t. So these three equations are one and the same, right? And that is our second equation. So for this one, why do you want to use this? Well, perhaps you are given an acceleration and a time, and you want to find out how much the velocity changed. Well, if that's the case, then v final minus v initial is equal to delta v, right? That's the change in velocity, and that's equal to a times t. So that's just from the first equation up here, right? And so you could have something like that where, again, you're given the acceleration, you're given the time, how much did the velocity change? And you just plug it in. All right. One more equation, and this is that v final squared is equal to v initial squared plus 2a delta x. And because I'm using x, I'm going to go ahead and put those subscripts back in. So what we're saying is that the final velocity in the x direction squared is equal to the initial velocity in the x direction squared plus 2 times the acceleration in the x direction times the change in the x position. Okay. Seems like a mouthful, right? And I'm going to write one more time, v final y squared is equal to v initial y squared plus 2ay, right? Probably negative 9.8 meters per second squared if we're talking about y, or acceleration in the y direction, and we multiply by delta y. Okay. Once again, two equations, one and the same. And as I mentioned before, perhaps you're looking at this saying, gee, that looks kind of strange, right? And the truth is, this equation, this set right here, set number 3, is super powerful because you notice that there's no time variable in it, right? There's no time variable in these equations. And so if you don't know anything about the time of an object's motion, you only know its initial or final velocity and then the acceleration and the change in position, you know those things, you can actually solve for one of the other variables, right? So you don't need the time depending on what things you're given. So if you're solving a physics problem and it's some sort of motion problem with constant acceleration, then consider for a second if it gives you any information about the time that the object is in motion. And if it doesn't, that's a surefire way to know that you are dealing with equation number 3 and you got to plug into there. Okay, I'm going to make one more comment because constant velocity motion is just a special case of constant acceleration. All right, what do I mean by that? Well, let's take this top equation right here. Okay, and I'm going to rewrite it at the bottom. So I have x final is equal to x initial plus v initial x times t plus 1/2 ax t squared. Okay, now if I have constant velocity motion, ax is equal to 0. So this whole term is canceled out. Okay, and we also said if it's constant velocity motion, v initial x is equal to v final x is just equal to v, right? It's just a constant velocity, so there's no point in writing all these subscripts, right? So then we get x final is equal to x initial plus v times t. And you will recognize that as the equation from the previous video where we talked about constant velocity motion. Okay, so as I said before, constant velocity motion, this is just a special case of this constant acceleration equation. All we're doing is we're saying, well, we take this constant acceleration equation, let's set ax equal to 0. V initial x is just a constant v, and then you have just derived, you've just solved for that equation for constant velocity motion. Okay, so for the purposes of this video, let's leave this off to the side for now, right? This is just a little reminder of, or just a little bit of understanding for why we got those equations from the previous video. Where do we pull those from? It just comes from here. Okay, what do you need to remember? Commit these equations to memory, right? At least one form of it, right? Because if you know one form, then you know all three forms. It just depends on, all that's changing is what subscripts you're pointing on or putting on, right? And so commit one form of each of these equations to memory, and you'll be able to solve for all these constant acceleration problems. And then also note and commit to memory the fact that the acceleration due to gravity is 9.8 meters per second squared.